Good afternoon, students. All right, we have about 20 students here. So today we are going to do more problems and examples on curve sketching. And if we have time left, we're gonna move to the next section, related rate. So while we are waiting for our friends, so we're gonna look at the review of curve sketching. Well, before doing that, any questions from anyone? Anyone have any questions today? All right. It seems like you just uh, finished physics class. So let's do a review first, and then we're gonna do examples like in 5 minutes. So for section 5.3 curve sketching, so last time we did one example. You can see that to graph the function, you need so many components. So the one that you need is going to be domains, intercepts, intervals of increase or decrease, local max and local min. So to find interval of decrease and local max and local min, here you're gonna need your first derivative, because the first derivative gonna tell you about increasing and decreasing properties, and also you can find the relative maximum from there. Does it make sense? So the second derivative gonna give you concave up or concave down properties. So in order to plot the graph, so you also need the second derivative, because you can see on what interval the function is concave up or concave down by looking at the second derivative. And also the last one, you need asymptotes. Well, because asymptote gonna tell you, the behavior when it touch plus or minus infinity. So last time I told you that, hey, we have vertical asymptote. So the vertical asymptote gonna be the one that the function approach plus or minus infinity at the point x equal to a. We're gonna call this thing vertical asymptote. X equal to a is a vertical asymptote when limit of the function f is plus or minus infinity when x approach a. So today we're gonna have more examples about vertical asymptote. And also for horizontal asymptote, well, this is the behavior when x go to plus infinity or minus infinity. So basically you are interested in how the graph behave when your x value is getting bigger infinitely, and also when x is super small, just go to negative infinity. So if it approach to a single number L, we're gonna call that y equal to L is a horizontal asymptote. So we're gonna have an example about horizontal asymptote today as well. All right. Last class I talked about how to plot the graph by looking at the first derivative and second derivative, and this is the example that we graph x to the fourth power minus 6x squared. Well, you can see that it is not easy, because we went through some components. We went through the first derivative, second derivative, and after that we combine it together. And then once we combine it together, we know the shape of the graph, and then we're gonna plot it at the end. All right, so today we're gonna do more examples. Are you ready? Well, we're gonna do 3 more examples. Example 112 is the first one for today. Ready? All right, let me see the roster now. So we have about 26 students, which is good. All right, any questions so far that you wanna know anything? No? All right, so let's do this one. Example 112. So for this question, I want to find, no, sorry, I have a function fx equal to e to the negative x squared. Well, I want you to sketch the graph of this function at the end, but we need to answer all questions first. So the first one, when I have fx equal to e raised to the negative x squared, what is our domain? So the domain gonna be just all real number, right? Well, when I say R here, this is mean all real number. So because I know that the possible value of x gonna be negative infinity to plus infinity. So x can be anything. Well, you plug in any number, so you can evaluate the function f. So now we're gonna find x-intercept and y-intercept. So again, to find x-intercept, if you want to find x-intercept, you let y equal to 0. Right? When you let y equal to 0, so what you have is 0 equal to e to the negative x squared. Is it possible that e to the negative x squared equal to 0? So the answer is, it is impossible, right? Because e to the negative x squared is always positive, right? Because the exponential function is always positive. So that means no x-intercept. Right? Because there is no way that you're gonna solve for x when y equal to 0. Sounds good? And then next we're gonna do y-intercept. So what is going to be our y-intercept? So y-intercept, we're gonna let x equal to 0. So when I let x equal to 0, so I have y equal to e to the negative 0 square, which is e to the 0, which is 1. So my y-intercept is going to be 0, 1. This is going to be the only intercept for this question, right? Because you have no x-intercept and you have just one y-intercept. So you can see that the idea is we are trying to collect more information, and at the end we're going to plot the graph. So let's look at number 3 here. So I need vertical asymptote and horizontal asymptote. So what is going to be my vertical asymptote? So that means I want to know is there any point that my function gonna hit plus or minus infinity? So usually to find vertical asymptote, you just need to look at the point that makes the function has denominator 0. Here, because your function is fx equal e to the minus x squared, so you have no vertical asymptote. No vertical asymptote. Right? The reason is because we don't have any point x equal to a that the function approach plus or minus infinity when x go to a. So no vertical asymptote. Well, if you do not want to memorize it deeply, you just memorize that. Well, the vertical asymptote happens when denominator equal to 0. So I'm gonna write the trick here. The trick is vertical asymptote exists when denominator equal to 0. For here, our function is not a fraction. You can see our function is not a fraction, so there's no way that your denominator is going to be 0. So no vertical asymptote. Well, what about horizontal asymptote? So you need to take the limit when x go to plus infinity. So what is going to be our limit here? So you can see that, well, when you have e to the something that is big, so when you plug in plus infinity, so you're going to get infinity square, which is going to be something big, and then you take negative, so it's going to be e to the negative infinity, which is going to be 0, right? E to the negative infinity, this is 0. Well, the same thing with limit when x goes to negative infinity, this is also 0 because no matter what, you square first and then you just take negative side. So on the power here that I highlight in light blue, this is going to be a negative number. Well, e raised to the very, very big negative number, this is going to be 0, right? Well, that means horizontal asymptote is y equal to 0, right? Because you have limit when x go to plus or minus infinity is equal to 0. Well, we're gonna save that thing and then we're gonna draw the graph later. So now next we're gonna compute the first and second derivative. So the first derivative, this is going to be e to the minus x squared times negative 2x, right? Because I use the chain rule, so I need to differentiate in the function negative 2x e to the negative x squared. All right, so f double prime x, this is going to be one more time. Take more one more derivative. So I'm going to pull out negative 2. And now I need to differentiate by using the product rule, right? So I'm going to will x times e to the minus x squared by as a product, and then I use product rule. So it's going to be x times e to the minus x squared times minus 2x. Well, this is udv, and then plus e to the minus x squared du, which is 1. So I just use the product rule. And what I have here, I have e to the minus x squared. So I pull out everything here, and then well, I have 1 second, I have negative 2 e to the minus x squared. So I pull out that thing. So I have 1 minus 2x squared inside the parentheses. Right, so this is just simplify. We just simplify the function. Sounds good so far? And then after that, we need all critical numbers and the interval of increasing and decreasing. So let's look at this thing. So we're gonna have f prime x equal to negative 2x e to the minus x squared. So here you can see that f prime x equal to 0 when x equal to 0, right? When x equal to 0, well, the first derivative is equal to 0. So that means your 0 is the critical point. Critical number, sorry. So let's figure out the sign of f prime. So when x is positive, and then you plug into that function, so you can see that e to the negative x squared is always positive. And if x is positive and negative 2 is negative, so here we're going to get negative sign. And then here you're going to get a positive sign, just the different sign on the different side. Sounds good? Well, which means the interval of increasing gonna be negative infinity to 0, and interval of decreasing gonna be interval of decreasing. This is going to be 0 to plus infinity. Here we go. And then all local max and local min. So for sure, this is increasing function, and then swap to decreasing function at the point x equal to 0. So that means when x equal to 0, we have a maximum, right? A local maximum. So which means a local maximum point is, well, when x equal to 0, so y equal to 1. Right? You know that when x equal to 0, you've already plugged in x equal to 0, so you get y equal to 1. So this point, this is also the intercept and also the local maximum point. So you just gain more information now. Next, we are going to look at the interval of concave up and concave down. So I'm gonna copy my second derivative here to the next page. Okay, I need to redo it again. 1 second. So I'm gonna copy this. Gonna copy this thing. All right, so this is my second derivative. For my second derivative, this is going to be 0 when the term that I highlight is 0, right? So which means 2x squared equal to 1. Well, this is the same thing when x is equal to plus or minus 1 over square root 2. Well, this is all candidate for inflection point. So if you look at f double prime here, so you have negative 1 over square root 2 and 1 over square root 2 here. So there are two candidates for critical point, for inflection point. And now you need to figure out the sign. So you can see that e raised to the negative x squared that I highlight in orange, this is always positive. And then you multiply negative 2, this is negative. So the term that I highlight in orange, this is all negative now. Well, when you plug in the number x in between negative, negative 1 over square root 2 and plus 1 over square root 2, for example, 0. So you're going to get the term that I highlight in green to be positive. Does it make sense? Let's say I just plug in number 0 here into the function here that I just draw the arrow. If I plug in x equal to 0 here, so I'm going to get 1 minus 2 times 0 square, which is 1. So the term that I highlight in yellow, it's positive. The term that I highlight in orange, this is always negative. So negative times, negative times positive. Well, this is going to be negative. This is how you figure out the sign. So this is going to be negative, positive, and positive. Sounds good? Well, you need to figure out the sign by yourself. And now when I have everything, so I'm ready to, okay, I need inflection point too. So number 8, inflection point. So all inflection points, they are the point that we change the concave up to concave down or concave down to concave up. So this is concave up, this is concave down, this is concave up. So, well, it means at the point x equal to negative 1 over square root 2 and the point 1 over square root 2 comma something. This is our inflection point. And when you plug in x equal to 1 over square root 2, so this is going to be 1 over square root e. How do I know that? So fx equal to e to the negative x squared, right? So I plug in 1 over square root 2. So this is going to be e to the negative 1 over square root 2 square root square. Well, this is e to the negative 1/2, which is 1 over square root e. All right. So you have everything that is ready to graph. So as I told you again, I told you last week that my technique is I'm gonna draw two real lines here. The first one gonna represent f prime. The second one gonna be f double prime. So my idea is I am trying to combine everything all together. And for the second derivative here, so I have the inflection point negative 1 over square root 2 and plus 1 over square root 2. So this is plus, this is plus, this is minus. This is for the second derivative. So for the first derivative, I have only number 0 here, which is, I'm going to put the critical number 0 here. On this side, I have plus, this side I have minus. So to combine these two together, so I'm going to draw 1 negative 1 over square root 2 here, 0 here, 1 over square root 2 here. And then once I do that, so I'm gonna look at the sign on each interval. So let's start from f prime first. So f prime, I know that everything below 0, that was the one that I highlight in orange, this is going to be positive. So this is going to be my positive thing, right? And then the one I highlight in yellow here, this is going to be my negative thing, right? This is negative, this is positive. So this is positive, positive, this is negative, negative. And then also on the f double prime, I know that everything in between negative 1 over square root 2 and negative 1 over square root 2, this is going to be negative. Everything else is positive. All right. We're almost there. And here we go. So now we have 4 pieces of the graph. So the first one below 1 over below x equal to negative 1 over square root 2. The second one is at x equal to 0. The third one at x equal to 1/2. So let's look at the shape. So the first one is plus and plus. This is increasing function. And also concave up. So this is going to be like that. Right? This is increasing function. Well, you don't have to write everything like me, but this is your second example. So I am trying to be slow. But on the exam, you don't have to draw everything like this. If you can go faster than me, you can go. But here, this is your first example. Like the second example, I'm trying to be slow for you. So this is increasing and concave down. It's going to be like that. Well, remember concave up, it's my concave down, it's just that. This is how I memorize it. And then this is going to be decreasing, and well, the second derivative is negative, so this is concave down. So decreasing and concave down. And the last one, this is decreasing and concave up. So it's going to be like that. So when you graph it, you're trying to just put all the shape here into the same graph, and then those will be easy. So the last one, well, now I want to sketch the graph of f. So again, the first thing that you need to sketch, this is going to be your axis, y and x. So first of all, let's try to put the intercept. So you know that here, today we have 0 and 1 here. This is our y-intercept. So you don't have x-intercept here. You have y-intercept 0 and 1. Well, you have vertical asymptote. This is y equal to 0. Going to be your vertical asymptote. Which means, well, asymptote gonna tell you that when x go to infinity, the graph should go to y equal to 0. I mean, should like go along the line y equal to 0. Well, the graph will not touch y equal to 0. And also when x go to negative infinity, so the graph gonna go like that. It's gonna just go along with the line y equal to 0, but it will not touch the line y equal to 0. Does it make sense? Well, here's because you have the vertical horizontal asymptote y equal to 0. Well, you already show that the limit when limit fx when x go to plus or minus infinity is 0. No, this is the main point of horizontal asymptote. And then after that, you can put your local max, local mean, and something. So your local max gonna be 0, 1. Well, this is your local max. Keep in mind, this is your local max. What else? So we have the inflection point, which is plus or minus 1 over square root 2, comma 1 over square root e. So I'm gonna just approximate it. So this plus or minus 1 over square root 2 and 1 over square root e, this is going to be our inflection point. Right? So this is negative 1 over square root 2. This is 1 over square root 2. And let's say this is 1 over square root e. It is less than 1, right? Like that, like that. Okay. Well, keep in mind that these two spots are going to be your inflection point. And this is going to be inflection point. Well, the next example, I'm going to go faster than this, but this is, I'm trying to be slow for you. Well, let's start doing that. Put everything into the same graph. So the first one, increasing and concave up. All right, let's do it. Well, it must be increasing on the left of x equal to negative 1 over square root 2. Here. How do I know that the graph going to be like this? Because, well, the function is increasing and concave up. And also, I have y equal to 0 to be my vertical asymptote. Well, the next one, increasing and concave down. So the graph going to be like that. All right. From negative 1 over square root 2 x square u to x equal to 0, I'm going to have a function that increasing but concave down. Perfect. And then next, well, decreasing and concave down, right? Decreasing and concave down. Whoop. Well, trying to make sure that this is concave down, all right? When you sketch it, it doesn't have to be perfect, but, well, it must be clear that this is concave down. And then also the last one is decreasing concave up. All right. Well, it's gonna be like that then. All right. This looks like a bell curve, which is, yeah, this is a graph of bell curve. So fx equal to e to the negative x squared. Sounds good. So we have everything we want. So local max, inflection point, well, fine, everything is good. All right, any questions? And this is your answer for this question. So you sketch the graph. Does it make sense? So any questions so far? We're gonna do 2 more examples on sketching. Well, just to make sure that you know the technique, how to do this one. This is going to be the big part of final exam as well, because you're gonna, the function is given and you will need to sketch the graph by using the property of calculus. All right. Any question? Type in the chat, please. Anyone? If you want to have any questions, I'll give you 30 seconds. No. Well, if you don't have any questions, so rate yourself then out of 10. So what is your score for your confidence now about sketching graph out of 10? Do you think if I give you a function, can you graph it? Well, out of 10, what do you think? What do you think? What you say 7? You need to be more confident. So more example then. Well, no opposite is in lead because he says 7.02. That is, well, if I cut off, well, he's gonna be A, right? And then 7 gonna be B plus. 7.3. All right. So it seems like you need more practice then, because you still like 6 and 7 or something. So let's do more example then. Is pi square bigger than 10? Pi square is 3.1. Could be bigger than 10. I'm not sure. Oh, that is the hard one. Oh, 9.85 for pi square. Woo. All right, so let's do example 113 then. So this is going to be the one that we're gonna plot the graph. So this is going to be a little bit harder compared to the previous example. Let's look at this example together. So we have the fraction now, well, which is good because this is going to be the example that we have vertical asymptote. So let's look at the domain. So what is going to be your domain here? Well, remember the domain is possible x value that you plug in and then you can compute f. Well, it's going to be everything except 1, right? Because you cannot plug in number 1 because number 1 going to be the value that make your denominator equal to 0. So what is your x-intercept and y-intercept? So for x-intercept, this is going to be, we can let y equal to be 0. That is 0 equal to x squared plus x minus, plus 1 over x minus 1 squared. So can we solve that thing? Is it possible that this is going to be equal to 0? So it's going to be 0 when that, right? And then how do I know that this is 0? What value of x will give me 0? So you can say that, hey, this is x squared plus x plus a quarter plus 3 over 4, right? This is x plus 1/2 square plus 3 over 4. Well, clearly on the right hand side, you have something that is bigger than 0, right? Because you have something square and then plus 3 over 4. So this is something bigger than 0. So impossible that you're going to solve for this thing. So no x-intercept. Well, you can say that x squared plus x plus 1 equal to 0 has no real roots. So that's the same thing. So if you use the formula, so you can see that you cannot solve for real number x. So the solution going to be complex numbers. So, well, anyway, no x-intercept. Well, for y-intercept, you can let x equal to 0 and solve for y. So if you let x equal to 0, then y equal to 0 plus 0 plus 1 over 0 minus 1 square. This is 1. Right? So, well, at the end, so you have, again, x equal to 0, y equal to 1. This is your intercept. Only 1 point. So now let's look at the vertical asymptote and horizontal asymptote. For this question, we are going to look at limit when x go to plus or minus infinity of x squared plus x plus 1 over x minus 1 square. This is going to be your horizontal asymptote. So what is going to be your horizontal asymptote? So you compute this limit and then you can see as you learn in chapter 1 that when you compute limit here, so the limit is 1. How do you know that? Because you have polynomial over polynomial, right? And then your highest degree on the top is 2, the highest degree on the bottom is 2. So you can see very quick that the limit is 1 because the ratio of the coefficient is going to be 1. So which means your y equal to 1 is your horizontal asymptote. What about your vertical asymptote? Well, you need to find the point that when you take limit, when x go to that number, well, you get plus or minus infinity. And this is going to be the one that the denominator of the function f equal to 0. Well, of course, this is x equal to 1. Why is that? Because when you compute limit of this function, where x go to 1 here, well, you're going to get plus or minus infinity, right? You don't know yet this is going to be plus or minus infinity. However, well, it's going to be infinity anyway. So that means because your denominator equal to 0, right? And then your numerator is going to be something that is not equal to 0. Well, that means x equal to 1 is your vertical asymptote, y equal to 1 is your horizontal asymptote. Well, you have more information about the graph now. So if you want to plot the graph now, you can just skip to the plot here, and then you can try sketching first. So I'm gonna draw the graph. and then that. Well, I know that this is y, this is x. I know that my y-intercept is 0, 1. Here, this is my y-intercept. And keep in mind that at the end, I am going to have y equal to 1 at my horizontal asymptote. And I need x equal to 1 as your vertical asymptote. At the end, when you plot the graph will not touch the asymptote, the vertical asymptote. It's gonna go along the vertical asymptote and horizontal asymptote. Well, we'll see that in a minute. Well, let's keep that thing, and then, well, let's look at the behavior of the first and second derivative. So on the exam, well, listen to me. On the exam, it is possible that we're gonna give you the first derivative and second derivative like this. So you don't have to differentiate by yourself because we are afraid that you're going to compute it wrong. So we're going to just give it to you immediately so you don't have to compute it by yourself. So this one, if you use the quotient rule to differentiate, so you're going to get f prime and f double prime. But to make you more convenient, we just gave you this thing, well, to avoid your mistake as well. And then now you already compute the first and second derivative. So our critical number is what? So we're gonna compute f prime x equal to 0 or f prime x does not exist. So usually we just do f prime x equal to 0, but for this question, it is a fraction, so we need to include the point that f prime x does not exist. So at what value of x, we can have the first derivative equal to 0. So this is going to be the point that x equal to -1, right? -1 gonna give you f prime equal to 0 because x plus 1 here. And then also you're gonna have x equal to 1 because it's gonna give you the denominator equal to 0. This is the point that gives you does not exist for f prime. So this is going to be your critical point. Critical number, sorry again, critical number. So you have critical number -1 and 1 here. So you want to figure out the sign of f prime. Again, you need to plug in the number. So you're gonna plug in any number after 1 here, plug it into the f prime function, and then you can see that you're gonna get negative value. How do I know so fast that this is going to be negative? So I can plug in any number, like for example, I plug in x equal to 10 million. So I'm going to plug it into this function. So it's going to be -3 times 10 million plus 1, and then over 10 million plus 1 cube. So you can see that this is going to give me a negative sign because I have two positive number as a ratio, and then I have negative sign in front. So that's mean I get negative here. So if I put any number between 0 and 1 now, let's say the easiest one is going to be 0, right? So you plug in 0, so you get positive 1. And then this you get -1. You can try to plug this number, and then you're gonna get your sign here. Well, keep in mind here, this is the special case when you compute the f prime because you cannot include the point x equal to 1 because x equal to 1 is not in your domain. Your domain is something, everything except 1. So we're gonna avoid the point x equal to 1. This is the point that, well, we do not include in our domain. So when you figure out your local max and local min, we just skip the point x equal to 1 because it is not defined. Right? The function is not defined at x equal to 1. So we're gonna have only the -1 here, which is you have negative sign on the left and positive sign on the right. So this is going to be your local min. So local minimum is attained. at the point x equal to -1. So let's compute that. So if x equal to -1, what is going to be your y? So f of -1, this is -1 square plus -1 plus 1 over -1 square. All right, so this is, I think, -1 over 4. No, not -1 over 4. It's going to be plus, sorry, because this is -1 square. So it's going to be plus 1 over 4. All right, a quarter. Good. So that is my local minimum. Good. Sounds good. All right. Well, if you feel like you want to put it into the graph, you can do it now. So when x equal to -1, so you have 1 over 4 here. Well, keep in mind, this is going to be your local min. Right? We're just trying to build up the graph one at a time. All right, so another one. So let's look at the second derivative here. So the second derivative that is given in the question is, well, 6 times x plus 2 over x minus 1 to the 4th power. So let's look at the behavior of this function. So how do I know that this is going to be, what is going to be our critical point, inflection point? So of course, f prime double prime x equal to 0 when x equal to -2, and f double prime x does not exist when x equal to 1. So your candidate is going to be -2, 1 here, but again, 1 is not in our domain, so we're gonna just keep it like that. Well, I'm gonna figure out the sign now. So negative, well, the thing that I highlight in yellow here, big number, so I plug in into that. So I get positive thing, right? And I have something between -2 and 1 here, let's say 0. So I plug in that. So I'm gonna get +1, right? Because 6 times 0 plus 2 over 0 minus 1 to the 4th power. So you can see that here gonna be positive anyway. So the sign of f double prime gonna just depend on x plus 2. This is negative. All right, so I have that. Here the interval of concave up. The interval of concave up. This is the one that you have positive sign, which is -2 to 1, union 1 to infinity. Well, you can see that I skip number 1 because, yeah, it's just not in our domain. And interval of concave down, this is going to be negative infinity to -2. Well, let's come back to this one. So I think I forgot to do the interval of increasing and decreasing, right? So let's do that. Let's do that. So interval of, well, I can say it here because I'm lazy. This is decreasing. All right, this is increasing. And this is decreasing. Well, I think you know how to, yeah, say it formally, so that's fine. Now state all inflection point. So for sure, this is going to be my inflection point. So when x equal to -2, well, I need to compute it again. So f of -2, this is going to be -2 square plus -2 plus 1 over -2 square, or -2, sorry, minus -1 square. So I just plug in number -2 into the function, and then what I got is 1/3. Right? It's going to be 3 over 9, which is 1/3. That means -2 and 1/3. This is going my inflection point. So -2 and 1/3. -2 and 1/3. Well, This is my inflection point. All right, now let's combine everything together. So we have, I'm gonna use the green pen here. F prime, F double prime. Well, let's start by F double prime. I have 1 here, -2 here. And then F prime, you're gonna have -1 and 1, right? So -1 here, 1 here. So at the point x equal to 1, this is not defined. So no x, no y value here. So it's undefined. And then you can see that, well, I can do that -2, -1, and then, well, the sign for f prime first is going to be plus between -1 and 1. Everything else is negative. So the sign of f double prime, it's going to be negative below -2. Everything else is positive. So the shape of the graph, decreasing concave down, decreasing concave up, increasing concave up, decreasing concave up. All right, so this is going to be the shape of the graph. Sounds good. Now, put everything together. So below -2, below x equal to -2, the graph should be something like that. All right. Well, the graph should be something like that, right? Below x equal to -2. Below x equal to -2. Graph should be something like that. However, we have y equal to 1 that control the behavior of x go to negative infinity. You cannot touch y equal to 1. So it's going to be something go like close to y equal to 1, but not, well, make sense? Well, which match with the decreasing concave, concave down, and then decreasing concave up on the next one. All right, decreasing concave up. Our scale is not that good, but decreasing concave up. Oh, as long as you label, this is fine. Well, I'm gonna move this thing up a little bit because what? Sorry. Move this thing up a little bit so it is out of our way. All right, next, from -1 to 0. So what happened? Well, increasing concave up. Tube. Well, easy. All right. Well, however, when x, well, this is just 0, right? Well, but go to 1, go to 1, go to 1, right? 1 is here. The graph just need to keep going, and concave up. Well, because our scale is not that perfect, so we cannot draw a nice, like, perfect graph, but this is good enough because we can see that when x from goes from -1 to x go to 1 here, you can see that the function is increasing and concave up. However, you need to pass the y-intercept at the 0, 1 here. Whoa. Just trying to be nice with the graph, but sounds good. Next, we have the last one. So we know that the graph must be decreasing and concave up when x is bigger than 1. So when x is bigger than 1, it must be increasing, decreasing and concave up. Well, because we have vertical asymptote here, so the graph cannot touch x equal to 1. Well, also the graph cannot touch y equal to 1. It forces you to have a graph like that. Well, and this is the graph of fx equal to x squared plus x plus 1 over 1 x minus 1 squared. Make sense? I don't think this is that too hard, but well, you just need to you know, compute all all jigsaw, and then you just all puzzles, and then at the end you just combine it together. Well, at least 10 points on the exam for one question. Well, you know, this is a big question for sure. All right, any question on this example? Any questions? So we're going to do one more example, and then we're going to stop sketching the graph and move to another topic. Well, if you are afraid that it's going to cut your horizontal asymptote, that's fine. The horizontal asymptote means you just care that the behavior when x go to infinity and negative infinity. So the graph can cut the horizontal asymptote, but you cannot touch it on the infinity thing, because this is the graph y equal to 1 is going to be the graph that control the behavior at infinity. Well, I maybe spoke it too fast. That's why you understand it wrong, I think. Well, hopefully you understand it, Ganpot. So, well, we include that one because 0 is x equal to 0 is in our domain. So we still need to include it. Well, if you screw up a little bit, you're gonna see that your local mean and inflection point not gonna be this point. But for this question, everything is perfect. So we just have here as for sure this is our local mean, and here this is also inflection point. All right, let's do example 114 then, if you don't have any questions. So the last one for this section. So example 114. So 2x minus 5 over x plus 2 squared. Ta-da! So here we're gonna look at domain, which is going to be real number minus a point 2. I'm gonna go a little bit faster for this example. So x-intercept, well, we're gonna let y equal to 0. So that's mean I have 0 equal to x minus 5 over x minus 2 square. Well, x equal to 5 over 2. Here we go. X equal to 5 over 2 and y equal to 0. This is our x-intercept. For y-intercept, so let x equal to 0. Whoa. Y equal to 2 times 0 minus 5 over 0 minus 2 square. This is y equal to negative 5 over 4. All right, so y-intercept is 0, negative 5 over 4. So let's look at vertical asymptote. So limit of x go to 2 to x minus 5 over x minus 2 square. Hey, this is plus or minus infinity, right? Well, we don't know yet, but this is going to be plus or minus infinity because x equal to 2 gonna make the denominator equal to 0. So it's gonna be some number over 0. So the answer is gonna be plus or minus infinity. Well, which means your vertical asymptote is x equal to 2. And then your horizontal asymptote is the one that you compute limit when x go to plus or minus infinity. Well, because the bottom is heavy compared to the top, so this is 0. Well, you can try divided everything by x squared, and then you're going to see that the limit is 0. Well, this is going to be y equal to 0. Well, you have to be fast on limit as well, and then you now get the f prime and f double prime because the problem is given for you. Now we're gonna look at our critical numbers. So f prime x equal to 0 when x equal to 3, right? Because we have 6 minus 2x on the top, and also f prime x equal to does not exist when x equal to 2. Again, when x equal to 2 here, it is not in our domain, so we are not going to plot it. Well, but x equal to 3, this is our critical point, critical number. Well, actually all critical numbers are 2 and 3. Well, but 2 is not in our domain anyway. All right. Here we have 2 and 3. This is f prime. Well, we're going to figure out the psi. So what is going to be our psi here? So for sure, when x is bigger than 3, so I can plug in any big number. So if I plug in, so let's look at the behavior here in red. So I have f prime equal to 6 minus 2x over x minus 2 cubed. If I plug in a very, very big number, like 1000, so I'm going to get negative over positive, right? So it's going to be, this is negative. If I plug in any number between 2 and 3, so for example, 2.5, so for the ratio of f prime, I am going to have positive on the top, positive on the bottom. So this is going to be plus, and this is going to be minus. Well, that's mean the interval of increasing is equal to 2 and 3. Well, the interval of decreasing, so I just make the abbreviation now, negative infinity to negative to 2, sorry, union 3 to plus infinity. All right, so I have everything ready to plot the graph. However, they ask you for max and min as well. So, well, x equal to 2, well, we just get rid of that thing because it is not in our domain. So we're going to look at x equal to 3. And at x equal to 3, this is going to be local max. How do you know that x equal to 3 is going to be local max? Again, this is increasing on the left of 3 and decreasing on the right of 3. So this is max. And then, well, when I plug in x equal to 3, y equal to 1, you can try it. So f of 3 is going to be 2 times 3 minus 5 over 3 minus 2 square, well, which is 1 over 1, which is 1. All right, so almost ready for the graph. Well, this is going to be the big one, as I told you. So it's going to take time, but well. All right, next I have f double prime here. Which is going to be, let me copy that one. So it's going to be 4x minus 14 over x minus 2 to the fourth power. Well, now f double prime x is equal to 0 when x equal to 7 over 2, right? And then f double prime x does not exist when x equal to 2. So for f double prime here, gonna have 2 and 3.5. Well, I'm gonna figure out the psi as well. So, well, the easy one is here that I highlight in light blue. This is always positive. So the psi gonna depend on just 4x minus 14, which is going to be plus here and minus all the way. So the interval of concave up. Well, when you look at me showing your work, showing work here, well, it is easy because I did this thing so many times. Well, for you, this is going to be your first time in calculus. Well, you're going to take more time compared to me because you are a beginner. So don't worry if you feel like, hey, Ajahn, I feel like this question, I spent 40 minutes on one question. It's pretty simple because that is your first time trying to do this question. So I can do fast because, well, I did this thing so many times, but for you, it's going to be, you're going to take some time to do this thing. Well, keep in mind, this is pretty normal. Well, once you practice, practice, and practice again, well, by the time that you take the final exam, it's going to be a lot better. So 2 times and comma 7 over 2. This is interval concave down. Well, so the inflection point going to be this point, right? 7 over 2. So 7 over 2. So I can plug in f 7 over 2, and then, hey, I can compute that thing. Well, it's going to be a little bit of computation to x minus 5 over x minus 2 square, and this is going to be 2 over 3 over 2 square, which is going to be 8 over 9. All right, good. All right, so I have everything ready to graph. So one more thing is going to be that f prime, f double prime, and then number 2 is going to be the one that we do not include in our domain. However, 7 over 2 is here. Well, for f prime, we have number 3, if you remember. Well, on the second derivative, well, we say that everything after 7 over 2 is plus, everything on the left is minus. Well, on f prime, you're going to have plus on interval 2 to 3. So 2 to 3, this is 2. 2 to 3 is just plus, everything else is minus. All right. Now we are ready. So if you look at the shape of the graph, so decreasing and concave down, increasing and concave down, decreasing and concave down, decreasing and concave up. All right, so your graph need to be something like that. Well, let's plot it. Y, X. All right, so take a step back. So first of all, what is our x-intercept and y-intercept? So x-intercept is 5.2, 0, and y-intercept is 0, negative 5 over 4. All right, this is going to be my x-intercept and y-intercept. You see, first one. All right, next is going to be my, what else? For me that I can draw it. So it's going to be intercept. Let's do intercept. Sorry, asymptote. So asymptote, we have x equal to 2 and y equal to 0. All right, so let's do x equal to 2 and y equal to 0. So x equal to 2, which is here, going to be a little bit before 2.5, right? X equal to 2, vertical asymptote. And then y equal to 0 going to be horizontal asymptote. All right. So the graph cannot touch x equal to 2. The behavior on infinity and negative infinity cannot touch x equal to 0, y equal to 0. So let's plot the local max and inflection point, and then trying to put everything together. All right. So local max 3, 1, 3, 1, body 3 and 1. All right. 3 is here, 1 is here. Okay. Okay, 1 could be something a little bit higher, right? Because negative 5 over 4 is there. Negative 5 over 4 is negative 1.25. So 1, okay, maybe here. Or I just, scale 3 and 1. All right. And then next, our inflection point. So keep in mind, this is our local max. Well, it's going to be inflection point on 7 over 2 and 8 over 9. All right, which is 3.5, 7 over 2, and 8 over 9, just something close to 1. All right. Now, put everything. Well, use the purple color now. So the first one, hey, it's going to be decreasing and concave down. Well, on negative infinity to 2, decreasing concave down. How? Decreasing concave down. Does it make sense? Well, decreasing concave down, but the graph cannot touch y equal to 0, so it must be like that, right? Because you cannot cross the y equal to 0, the line y equal to 0, because if you do, the horizontal asymptote is not going to be y equal to 0. Well, and also because x equal to 2, you have vertical asymptote. Well, it must be the case that the graph just go down like that. And also you have to pass this point, because this is 0 and negative 5/4. This is y-intercept. All right, next we're going to look at the behavior when x equal to 2 to x equal to 3, right? We say that when x from 2 to 3, we have increasing but concave down. Okay, I have to part this one, right? All right. Beautiful. And the next from 3 to 3.5, well, it must be decreasing and concave down. Oh, this is easy one. Oh, I need to make sure that this is like a curve. And the last one is decreasing and concave down. Concave up, sorry. Here we go. And this is the graph fx equal to 2x minus 5 over x minus 2 squared. How do you feel? Yeah, we are done with this question. So, well, this is what I expect you to do on the exam. So you should be able to do it. And well, I should say start this question or the previous one. Well, this is going to be our perfect candidate for the exam. All right, so I'm gonna answer the question in the chat. So any question? How can the line pass the vertical asymptote? Okay, so again, vertical asymptote, the horizontal asymptote y equal to 0, you can pass it, but at behavior at the infinity, you cannot touch it. Does it make sense? Because when we do the horizontal asymptote, we say that limit to x minus 5, x minus 2, when x go to plus infinity. So this is 0. So which means we are interested in the behavior at x go to plus infinity. This is 0. So when x go to plus infinity, this is 0. So we don't care when x equal to 5/2, it's going to pass this thing or not. And also when limit of x go to negative infinity, this is also 0, right? Hey, whoa, is that my function here? Okay. X squared, yeah, this is also 0, sorry. I talk a little bit because I forgot square. Okay, 0, and then here you can see that, well, the behavior when x go to negative infinity, this is 0, so the graph go to 0. So we didn't say anything that when x is in between like negative 5 to 5, the function cannot pass y equal to 0. No, we didn't say that. Why do we have to find limit when x approach? So the reason why I find limit x go to 2, this is because when you have this function, we need to find the point, well, 0 pop, we need to find the point that your answer gonna be plus or minus infinity. So what is going to be your candidate here? So I say, hey, well, if I want plus or minus infinity, I need the denominator to be 0, right? So that's mean, hey, that question mark number must be 2. So that's why I compute limit x equal to 2 to check that this is going to be a vertical asymptote. So I can draw the line here, the dashed line here, when x equal to 2. And then, hey, actually, this is, you can see from the graph that this is negative infinity. So it's going to go to negative infinity. All right. Sketching graph is the one that you need to practice for sure. For sure. Everyone, for sure. Here, this is going to be your practice. Example 115, 116, 117, 118, and also your homework. Going to be one big question, 15 point of your homework, which is going to be half of your homework for ask you to sketch the graph. So you should be able to draw off this thing, sketching of those graphs. Again, solution going to be provided on my channel, so you can go to my channel and look at the solution of this example after.